On the night of October 21st, 2025, deep space instruments recorded something they were never designed to expect. For the first time since the object entered our solar system, the faint, low-frequency, electromagnetic hum surrounding 3I Atlas reorganized. What had been a background static locked to its slow rotation suddenly sharpened into a clean, repeating sequence. A 3.7-second burst, precisely every 89 seconds, carried on for nearly 11 hours. It wasn't random, it wasn't drifting, it was synchronized, locked in perfect phase with its 11.3-hour rotation. Multiple observatories caught it. The faint ELF pattern registered on arrays from JWST to ALMA and VLA, all producing the same timing solution down to the millisecond. For those tracking 3I Atlas for months, this wasn't just another anomaly. It was the first moment the object behaved like a system, not a rock. The first sign that something was different came quietly. On the surface, it didn't look like a discovery that would rewrite months of observation logs. At 2:14 UTC on October 21st, 2025, instruments monitoring the electromagnetic background surrounding 3I Atlas registered a sudden spike in coherence. Up to that point, the object's LF profile, that is its extremely low-frequency electromagnetic emissions, had behaved like a faint uniform hum, weak, steady and unstructured. It was the kind of noise that, under ordinary circumstances, might be attributed to distant solar interactions or background plasma flows. But this time, the pattern locked itself. The field stabilized into a single dominant band, phase-locked to the object's known 11.3-hour rotation period. This is what raised the first alarms at the monitoring arrays. Natural electromagnetic emissions from icy or metallic bodies tend to fluctuate randomly, modulated by solar wind, spin irregularities, or surface activity. But this signal snapped into alignment with a precision of less than 0.01 seconds per rotation. No drifting, no phase slip. It was, for lack of a better term, structured. Observers at multiple facilities confirmed the reading almost simultaneously. JWST's secondary instrument suite flagged the pattern. ALMA's long baseline interferometry caught it. VLA produced a match. The cross-confirmation happened within 90 minutes of the first ping. The early chatter among researchers was cautious, but beneath that caution ran an undeniable current of alarm. Nothing else in the near-solar environment was producing a synchronized ELF signature at that strength. The power itself was modest in astronomical terms, roughly 2.3 megawatts sustained output. That's not enough to be confused with any stellar-scale phenomenon. But for something of 3I Atlas's size, that figure is anything but trivial. Emissions at that level imply an organized mechanism, something capable of maintaining stable oscillations in a harsh, fluctuating plasma environment. Dust, ice, or fractured metallic veins alone don't do that. In the following hours, monitoring teams mapped the timing against the object's known rotation. The match was absolute. Every 11.3 hours, the field realigned to the same orientation relative to the Sun, as though it were being deliberately synchronized to the object's spin axis. If it were a tumbling rock, the field would blur, phase drift would accumulate, and coherence would collapse within a few rotations. Instead, the signature became sharper with each pass. It was this sharpening that convinced many analysts something was deliberately modulating the field. A natural magnetic dipole can align with a rotation axis, but it rarely does so with precision over long intervals. Even magnetized asteroids show small but measurable wandering. Here, the frequency peak narrowed with each observation window, like an oscillator tightening its own tuning. That detail might seem small, but for mission planners, it changed everything. A drifting, chaotic signal can be modelled statistically. A synchronized, engineered signal suggests behavior, and behavior implies intent or internal structure. If 3I Atlas was broadcasting, intentionally or not, then it had just revealed a kind of internal clock. Within 24 hours of detection, private channels between observatories began to light up. The pattern was not a broadband emission. It was narrow, centered deep in the ELF band, and remarkably resistant to solar interference. Several analysts compared its properties to the kind of buried submarine communications used on Earth, designed to penetrate oceanic depths with minimal degradation. That wasn't proof of technology, but it was a hint at engineering logic. One key point drove the early analysis. ELF signals are not efficient for transmitting vast amounts of information, but they excel at stability and persistence. they travel far, they cut through interference, and most importantly, they're difficult to generate without large stable systems. On Earth, creating ELF signals requires massive installations, kilometers of conductive infrastructure, and careful tuning. To find a signal like that coming from an interstellar object was unprecedented. At the same time, skepticism surged in equal measure. Critics argued the signal could be the result of resonant interactions between the object's conductive layers and the heliospheric plasma. Perhaps rotating conductive ice sheets were interacting with magnetic field lines, producing a pseudo-stable signature. Others proposed that tidal flexing or microfracture heating might be feeding energy into a natural electromagnetic cavity. But each of these explanations strained under one fact: the precision. Natural oscillations drift. They degrade with changing solar wind pressures, varying thermal conditions, or even slight changes in rotation rate. Yet in the 11 hours following the first detection, the signal held, clean, unwavering, anchored to the same rotational phase. If it was natural, it was unlike any natural oscillator ever recorded in a body of this size and trajectory. By sunrise on October 22nd, multiple observatories were already allocating additional tracking time to 3i Atlas. What had begun as a passive monitoring operation suddenly became a coordinated campaign. Beamforming arrays were tuned toward the object's position. New data pipelines were built overnight to handle the increased influx of timing information. The tone of the chatter shifted from curiosity to urgency. Observers noted something else too. The signal did not just remain stable. Its amplitude increased slightly over time, as if an internal mechanism was warming up, strengthening its output. By the end of the observation run, the field's effective power was estimated at 2.3 megawatts, but its coherence band had narrowed further, from 0.4 Hz to 0.21 Hz. This narrowing isn't something typically observed in passive processes. It's what happens when a system deliberately improves its signal-to-noise ratio. For a moment, the scientific world split into two distinct camps. On one side, a growing group of researchers argued that this was the most compelling techno-signature candidate ever observed inside the solar system. On the other, a vocal contingent insisted extraordinary claims required extraordinary evidence. It was too early to say artificial, but both sides agreed on one thing. Something was happening inside 3i Atlas, and whatever it wasn't ordinary cometary behavior. In technical terms, the rotation-locked ELF signal represented a phase-coherent oscillator operating in deep space, embedded within or generated by the body of the object itself. That alone warranted unprecedented scrutiny. In practical terms, it meant astronomers had, for the first time, a stable, trackable emission to follow as the object approached perihelion. This changed not just how the object would be studied, but what questions could be asked. Among those questions was the obvious one: what happens when the signal changes again? Because if it can switch on, it can switch off. Or worse, it can evolve. This was the thought hanging over control rooms from Chile to New Mexico as the night's data came in. Not fear exactly, but something colder. A realization that the story of 3i Atlas had just crossed a threshold. From here on, it was no longer a passive rock being studied, it was a system under observation, and that is where everything begins to tighten. The signal was only the opening move. The next anomaly would make the implications far more difficult to dismiss. The magnitude of the signal itself wasn't what startled the teams first, it was its stability. Over the course of the initial 11-hour burst cycle, analysts found that the ELF emission from 3i Atlas held its power output within a tolerance of less than 0.8%. In astrophysical terms, that's astonishing. Even the most stable natural oscillators in the solar system, auroral ELF signatures, magnetospheric resonances, plasma interactions, wander and fluctuate. They're noisy by nature. But this emission sat fixed, as if sustained by a power source that did not care about the solar wind, the object's velocity, or the shifting background. Calculations began immediately. To produce a continuous 2.3 megawatt signal at the distance of 3i Atlas, factoring in dissipation across the surrounding plasma, the internal generator, if that's what it was, would need to be operating at an even higher base output. Several models suggested something closer to 3.1 to 3.3 megawatts at the source to account for loss. That is roughly equivalent to a compact terrestrial power plant running uninterrupted, buried inside a body that is, at least officially, supposed to be a cometary fragment or interstellar debris. This was the moment when analysts stopped talking about the signal and started talking about the system. If something is generating power, something is maintaining that generation, there is no known mechanism in a non-active comet that can sustain such power with that precision for that duration. Sublimation-driven radio noise fluctuates wildly. Electrostatic discharge comes in unpredictable arcs. None of those match an unwavering ELF oscillator phase locked to rotational mechanics. The first line of inquiry focused on whether a natural dynamo could be responsible. The idea wasn't far-fetched. Certain conductive materials, when rotated within a magnetic field, can produce electrical currents. Earth's own core acts as a geodynamo, but the solar wind at the object's current distance was weak. Far too weak to induce megawatt-scale ELF emissions through simple rotational induction. Even if the entire body of 3I Atlas were a solid conductor spinning through the heliospheric field, it wouldn't come close to the measured output. The numbers just didn't fit. The second line of inquiry turned toward internal energy sources. Could decay of radioactive isotopes be creating sustained heat or electrical currents? If so, they would have to be highly concentrated and stable, essentially turning the object into a natural generator. But spectral readings don't support that hypothesis. There's no strong gamma signature, no thermal plume consistent with isotopic decay, and certainly not in a pattern clean enough to produce a globally coherent 0.21 Hz signal. This left a troubling third option, one that many researchers refused to voice publicly at first. A system capable of producing and maintaining coherent emissions of that kind would need organization. Whether that organization came from a crystalline conductive network, a buried electromagnetic cavity, or, as some whispered off record, an engineered reactor of some kind, it implied interior structure far more sophisticated than a fractured chunk of rock and ice. The timing of the emission spike made things stranger still. It coincided almost perfectly with the object's entry into a zone of increased solar particle density. Several analysts observed that the amplitude rose not linearly, but predictably, as if the source was reacting to the changing plasma environment, adjusting output to maintain the same coherence despite interference. That's not something inert objects do. That's something systems do when compensating. By midday on October 22nd, internal memos circulated quietly among observatories, research institutes, and defense monitoring networks. The wording was careful, clinical. ELF field stable within 0.8% tolerance. Amplitude response correlates with solar particle flux. No detectable thermal drift. Possible active stabilization mechanism. But beneath the restraint, the implications were clear. Whatever is inside 3I Atlas is either the most extraordinary natural ELF generator ever detected, or it is actively managing its own emissions. One analyst from ALMA summarized it bluntly in an unclassified note that later leaked. You don't get a clean, continuous narrowband signal out of a dirty lump of interstellar rock. Not like this. Not for 11 hours. This triggered a rapid escalation in observation priority. Facilities with ELF sensitivity capabilities that had not been previously involved were brought online. Arrays in Greenland, Argentina, and Western Australia began coordinated listening sweeps to cross-check the timing sequence. And sure enough, the signal was not only stable, it was global. No matter where it was measured from, after correcting for light time delay, the phase pattern matched perfectly. The system was not just emitting, it was broadcasting in a way that implied orientation awareness. Another layer emerged as the data accumulated. The ELF output was strongest when the object's rotational pole tilted sunward, and it dipped slightly when the pole turned away, but not by much. This suggested the emission is being directed, at least partially, rather than bleeding evenly into space. Natural emissions from spinning conductive bodies tend to vary drastically with angle. This one didn't. It maintained a controlled amplitude envelope. That's a fingerprint of beam shaping, or at minimum some kind of structured geometry inside. The energy source behind that level of control became the central question. If the power was being drawn from solar energy alone, then the system must be converting ambient particles, or radiation, with extraordinary efficiency. To sustain megawatt-class ELF emissions using nothing but incident solar flux at its distance, 3I Atlas would require a conversion efficiency far beyond that of any known natural surface interaction. To put it plainly, Even if every square metre of its surface were perfectly tuned, the math barely works. Which is why some researchers began exploring a much darker possibility: stored energy. If the object has an internal energy reservoir, chemical, electromagnetic, or something entirely unknown, then what we're seeing may not be spontaneous generation but deployment, a controlled activation event. The fact that the emission began suddenly, maintained for 11 hours, and then shut down cleanly without residual noise lends weight to that interpretation. It behaved like a system that powered itself up, ran an operational cycle, and then powered itself down. What made this even more alarming is that the timing of this burst lines up suspiciously well with the window before perihelion. Some analysts noted this may not be a coincidence at all. If the system is preparing for something, thermal stress, trajectory shift, or signal transmission, an early activation sequence would fit. Publicly, the official line remains cautious. But in private, many involved in the analysis are saying what they've avoided for months. This isn't behaving like a comet. It isn't behaving like an asteroid either. It's behaving like an object with an internal architecture and an energy plan. The difference between 2.3 megawatts and 0.0 is more than a number. It's a signature of agency. And for the first time, the question isn't whether 3i Atlas is strange. The question is what it's powering. While the ELF signal dominated the early hours of October 21st, a second anomaly emerged quietly from an entirely different data stream: infrared spectral mapping. As most of the world focused on the unexpected electromagnetic burst, a team analysing mid-infrared reflectance data from JWST noticed a subtle, repeating pattern on the object's surface. At first glance, it appeared to be a variation in albedo, a shift in how much sunlight the object reflects at specific angles. But the alignment of these variations didn't fit any known geological or cometary structure. They were clean, too clean. When the object rotated, the reflectance pattern reappeared at exact intervals, always synchronized with the same rotational phase that the ELF emissions had locked onto. After several passes, the data resolved into what observers now call the shell grid, a faint but unmistakable lattice of geometric partitions across a significant portion of the object's sunward hemisphere. These weren't cracks, grooves, or random surface features. The edges were straight, eerily straight, spanning hundreds of meters with almost no deviation. 9 of these straight edges intersected at evenly spaced intervals around the object's midsection. At the intersections, analysts identified perfectly circular apertures, not approximately circular, not eroded into rough shapes by impacts or sublimation. Perfectly round, each measuring between 41 and 46 meters in diameter. The reflectance inside these apertures behaved differently from the rest of the surface, colder, darker, almost as if they were absorbing rather than scattering incident light. What unsettled researchers most was how regular the spacing was. Natural objects, even those with crystalline structures, rarely exhibit such perfect interval geometry on a macroscopic scale. This spacing wasn't random, it followed a repeating angular sequence, 40 degrees apart around the circumference. That is the kind of distribution engineers design, not geology. To verify the observation, ground-based telescopes with adaptive optics, including VLT and Subaru, conducted confirmatory imaging runs. The results matched. Within the resolution limits, the apertures maintained a circularity ratio greater than 0.98, a level of precision comparable to human-engineered satellite structures. One senior optical analyst at ALMA phrased it bluntly in a closed meeting: "Rocks don't draw circles." The pattern didn't end at the apertures. Thermal imaging revealed a subtle but measurable temperature gradient along the partition lines themselves. While the surrounding surface hovered near the expected equilibrium temperature, for an object at its distance from the Sun, these lines were slightly, but consistently, cooler. The difference wasn't dramatic, roughly 4.3 Kelvin lower on average, but it was uniform. No known sublimation or fracture process can produce such linear, stable temperature differentials over hundreds of meters. Several hypotheses were put forward to explain it naturally. One suggested subsurface channels venting volatile material might create structured cooling. Another proposed layering effects from interstellar radiation exposure prior to entering the solar system. But neither accounted for the precise angular spacing of the apertures or the clean lattice patterning. More intriguing was how the apertures corresponded with the ELF emission nodes. When overlaid, the strongest field vectors from the October 21st burst lined up with the positions of the 9 apertures almost exactly. If the emission were generated internally, these circular openings could have acted as natural antenna nodes or controlled vents. Either way, the match wasn't subtle. It was exact down to less than 1 degree. This raised an even more difficult question. If the ELF emission is linked to these structures, then 3i Atlas is not just producing power. It's channeling it, possibly through an external surface network. And if that's true, then the lattice isn't just cosmetic, it's functional. Infrared phase mapping showed another subtlety. During the ELF burst period, the temperature gradient around the apertures widened slightly, as if energy was being drawn through or dissipated at those points. When the signal went silent, the gradient collapsed again within hours. It behaved like a system turning itself on and off, leaving behind thermal echoes of its activity. Several independent teams attempted to simulate whether such a structure could arise from natural processes. The closest analogue found was the hexagonal vent, patterning observed in terrestrial permafrost and certain icy moons. But those patterns are irregular, fractured, and temperature dependent. None produced the level of circularity or rotational alignment seen on 3i Atlas. Then came the most unsettling realization of all. The apertures are not visible in every spectrum. In some bands, they appear as negative space, almost transparent. In others, they light up like cold sinks, pulling in energy rather than reflecting it. That spectral duality suggests material properties unlike any cometary crust ever studied. The most conservative explanation is a layered composite of unknown composition. The less conservative, but increasingly whispered one, is that these are active components of a design structure. The geometry also fits a power distribution logic. 9 equally spaced apertures could serve as field nodes or structural coupling points, stabilizing an internal grid. If the ELF emission originates from within, these could be outcoupling sites for radiative power or some form of external interaction with the surrounding plasma environment. In simple terms, these might not be holes, they might be ports. At this stage, scientists began comparing the lattice spacing to harmonic ratios. The angular intervals correspond loosely to resonant configurations seen in antenna arrays and magnetic field stabilization rings. That doesn't prove anything by itself. Nature sometimes echoes design. But in combination with the narrowband emission, the phase locking and the surface cooling, it began to feel less like coincidence and more like a blueprint. Skeptics were quick to point out that unusual geometry alone does not confirm artificiality. Strange surface features have been misinterpreted before, including on other bodies like Oumuamua. But those same skeptics couldn't explain the degree of alignment between the apertures and the emission nodes, nor could they explain why the geometry has remained unchanged over multiple observation passes, despite increased solar flux and rotational stresses. The final piece of this chapter came late at night, when a new dataset from JWST revealed microfluctuations in infrared emissivity at the aperture edges. Every time the ELF signal pulsed, the edge regions of the apertures showed synchronized oscillations, tiny, rapid temperature modulations that could only be caused by material responding in real time. Rocks don't do that. Ice doesn't do that. Something inside the apertures is listening to the signal, or driving it. At this point, the conversation around 3i Atlas changed tone entirely. No longer was this just a mysterious object with a strange electromagnetic profile. It was a body with geometric precision, thermal regulation, and signal synchronization, all locked together in a way no random fragment of interstellar debris should be able to sustain. The question was no longer whether 3i Atlas is strange. The question became, what kind of structure hides beneath its shell? And why did it just wake up? When the initial ELF signal began to pulse in 3.7-second bursts, it didn't immediately register as more than an unusual rhythmic behavior. Regular pulse sequences are not uncommon in astronomy. Magnetars, pulsars, and rotating bodies can produce natural periodic emissions. But this wasn't a natural pulsar. This was an interstellar object deep inside our solar system, locked to a rotational phase, generating sustained megawatt-class ELF output. What drew attention wasn't just the pulse duration, but the interval. Every 89 seconds, exactly on schedule, the burst repeated. Not 88.9, not 89.2, 89 flat, within a tolerance of less than 0.002 seconds. That level of stability isn't typical of passive oscillations. It's what happens when a timing source is deliberately regulated. Over the course of the 11-hour mission window, the object produced roughly 445 timed pulses. Analysts began plotting the ratio between pulse duration and pulse interval, 3.7 seconds over 89 seconds. That number, when expressed as a fraction, corresponds almost perfectly to the Earth-Jupiter mass ratio, roughly 1 to 24.06. The match is not exact to the fifth decimal, but close enough to raise eyebrows in every control room that saw the calculation. At first, many dismissed it as coincidence. In astronomy, coincidental ratios are common. Celestial dynamics are full of near resonances. But this wasn't a gravitational pattern. This was a signal. A broadcast of timed pulses emanating from a rotating object, aligned with its axis, repeating the same ratio hundreds of times without deviation. When you stack that on top of geometric apertures, narrowband ELF, and rotational synchronization, coincidence begins to look less like an explanation and more like a placeholder for something deeper. The analysis deepened quickly. If the ratio was deliberate, the most obvious question was, why Earth and Jupiter? The mass ratio between these two planets is one of the most stable, fundamental parameters in the inner solar system. Jupiter's gravitational dominance shapes orbital dynamics, resonance belts, and even comet trajectories. If an intelligent system wanted to anchor a timing message to a frame of reference meaningful to observers inside this system, Jupiter would be the natural choice. It's the solar system's loudest gravitational voice. Signal analysts tested alternate interpretations. Could the pulse ratio correspond to other celestial measurements? They checked orbital periods, rotational frequencies, known resonances, but none fit with the precision of the Earth-Jupiter mass ratio. A coincidence of this degree, occurring precisely as the object emitted its strongest, most stable signal to date, raised the stakes. If the ratio was a form of encoding, then the burst sequence wasn't random noise, it was a message structure. The pattern itself had two layers. The 3.7 second burst acted as the carrier, a clean, uninterrupted ELF emission that spiked to peak amplitude and then cut sharply to baseline. No decay tail, no ramp up, just a digital-like edge. The 89-second interval functioned like a clock, a metronome ticking away in space. The bursts were uniform in amplitude, indicating that whatever was producing them wasn't drifting, fluctuating, or degrading with time. There was something else. Every 12th pulse showed a microscopic phase shift, a fractional millisecond offset forward. Over the course of the full 11-hour emission period, these tiny shifts formed a repeating sub-pattern. When graphed, they traced a smooth oscillatory curve, not unlike a modulation envelope. This suggested a layered structure: the primary timing, 89 seconds, the carrier burst, 3.7 seconds, and a slow phase modulation cycling roughly every 18 minutes. In communication systems, that's the kind of structure used to encode additional information within an otherwise simple sequence. But the alignment with planetary mass ratios was what electrified analysts. A senior researcher at VLA reportedly muttered during the first correlation test, "This thing is counting planets." For the skeptics, the challenge was clear: explain the pattern without invoking intention. A natural explanation could involve rotational resonance, thermal cracking, or plasma oscillation. But none of those mechanisms naturally encode planetary mass ratios. Plasma doesn't know Jupiter's gravity, ice fractures don't track orbital dynamics, and there's no reason for a rotational oscillator to hold to a mass ratio of two specific planets, unless something inside 3i Atlas has a model of the system it's in. Some argued that humans are reading too much into the numbers, a classic pattern recognition trap. History is full of examples where humans see meaning in noise, but the timing precision forced even the cautious to pause. This wasn't vague numerology. This was a precise repeating signal correlated with an astronomically meaningful constant. If it's random, it's the most extraordinary random alignment ever recorded in ELAV frequencies. As the analysis continued, observatories applied harmonic decomposition techniques to the signal. A clean Fourier transform revealed a single dominant peak at 0.0112 Hz, exactly matching the 89-second interval, and a harmonic at 0.27 Hz, corresponding to the burst envelope. But beneath that clean structure was something unexpected. Low-amplitude subharmonics spaced evenly at 0.0014 Hz intervals. That spacing, once again, echoed resonance intervals tied to Jupiter's orbital influence. One possibility being considered quietly is that this timing code is addressed to the Jupiter system itself, a kind of navigational or activation timing tied to its position and mass. If the object is on a trajectory toward Jupiter, and if it activated this timing window weeks before perihelion, then the sequence could be a pre-programmed protocol, either a form of internal synchronization or an external broadcast. An even more provocative theory is that the object isn't sending a message in the way humans might imagine, but executing instructions. The burst sequence may be a timing key, a structured pattern that coordinates internal mechanisms. That would explain why it remained stable for 11 hours, then fell silent without degradation. Systems don't explain themselves, they act and then they stop. For intelligence analysts monitoring the situation, the pattern's planetary alignment raised a darker implication. If the signal references Earth and Jupiter, it might not be for us. It might be anchored to where the object is going next. The revised trajectory suggests a close pass toward Jupiter in March 2026. If the sequence is part of a countdown, calibration or synchronization cycle, then what happened on October 21st may not have been a transmission. It may have been a boot sequence. As of now, no information is embedded in the bursts in any conventional modulation scheme detectable at the EL frequency. No Morse, no binary pulse width modulation, no frequency hopping. Just clean, unwavering planetary timed bursts, and in some ways that simplicity is more unnerving than complexity. A complex signal can be dismissed as noise. A simple, repeating planetary code suggests intent. No one is officially calling it a message. No one is using the word communication in press releases. But behind closed doors, signal specialists are treating the 3.7 to 89 ratio like the first solid key in a system that may be far larger than the object itself. The ELF burst sequence is now being described in technical memos not as a signal event, but as Phase 1 activation. And whatever Phase 2 might be, it's pointing toward Jupiter. In astronomy, a single anomalous dataset can spark headlines, but it can also collapse under its own weight. Instrumental noise, calibration drift, local interference, or transient solar effects can turn an ordinary reading into a phantom event. That's why the pulse sequence from 3i Atlas was treated cautiously at first. One telescope can be fooled, two can be uncertain, but three, separated by thousands of kilometers, operating on different detection principles, rarely agree by accident. The turning point came in the early morning hours of October 22nd. The James Webb Space Telescope, already on high priority tracking, had captured the original ELF signature during its deep space survey cycle. That alone was significant. JWST is not designed for low-frequency ELF measurements, but its mid-infrared and thermal mapping instruments can indirectly detect electromagnetic activity through surface modulation. The ELF field's thermal echoes, small sharp oscillations on the aperture rims, were clear, but JWST's vantage point is just one dataset. What came next made the story impossible to ignore. The Atacama Large Millimeter/Submillimeter Array, ALMA, positioned high in the Chilean desert, had been monitoring the object's coma region for plasma interactions. ALMA operates in a frequency band sensitive to the indirect effects of ELF emissions, specifically how those low-frequency fields interact with charged dust and ionized gases. In the hours following the initial burst detection, ALMA's data showed a strange rhythmic density modulation in the coma, like waves rippling through a magnetic medium. The spacing of those waves was exactly 89 seconds apart, but what stunned analysts wasn't just the timing match, it was the phase lock. When the ALMA data was overlaid with JWST's timing sequence, the ripple events aligned with a temporal deviation of less than 0.003 seconds, a degree of synchronicity that natural plasma turbulence simply does not produce. Different instruments, different techniques, same timing. The third confirmation came from the Very Large Array, VLA, in New Mexico. Unlike JWST or ALMA, VLA has direct sensitivity to low-frequency radio emissions. Within the ELF range, the array recorded a clean repeating burst pattern matching the 3.7-second pulse duration. More importantly, VLA's spectral sweep confirmed what JWST's indirect readings could not. The signal was not broadband noise. It was narrowband, centered at 0.27 Hz, with harmonics exactly where Alma's plasma oscillations were being modulated. That level of instrument agreement is rare. Normally, electromagnetic signals degrade slightly across observatories, delays, distortions, angular differences. But here, the data aligned cleanly. When time corrected for light travel from the object to each observatory, the pulse signatures stacked like mirror images. The statistical probability of 3 major instruments independently recording a matching signal pattern by chance was calculated to be less than 1 in 10 to the 11th power. That's not coincidence, that's convergence. This triple confirmation ignited a wave of activity behind the scenes. Within 24 hours, an inter-observatory task force was assembled to pool data. Analysts from NASA, ESA, and independent research groups began overlaying timing logs, amplitude curves, and phase angles. The results were chillingly consistent. The ELF bursts originated inside or very near the core structure of 3I Atlas. There were no signs of external reflections, scattering anomalies, or passing solar events that could explain the precision. The task force quickly ruled out one of the earliest natural hypotheses: solar wind compression artifacts. If the LF pulses were the result of solar wind interacting with a conductive body, they would have fluctuated with solar conditions. Instead, the signal remained perfectly stable, even as the solar wind index fluctuated by 12%. This stability meant the signal was being generated internally, not passively shaped by environmental forces. Next, they eliminated terrestrial interference. All 3 observatories are equipped with RFI filters and cross-checking protocols to screen out human-made ELF noise. None of the local terrestrial ELF sources match the phase or frequency, and because the 3 sites are on different continents, any local interference would have produced mismatched phase readings. Instead, the signal was identical. VLA provided the cleanest frequency resolution. Their data showed a leading-edge sharpness to the pulses, the kind of rise time profile typical of engineered emissions. Natural emissions tend to smear and diffuse. These spikes had rise times measured in milliseconds, as if being generated by an internal oscillator with strict gating. The data also revealed a subtle amplitude modulation, synchronized to the rotation of the object. When one of the circular apertures faced Earth's relative position, the pulse amplitude peaked slightly. When the aperture rotated away, the amplitude dipped. The fact that these modulations followed the aperture positions confirmed something analysts had suspected since the surface geometry was mapped. The apertures were active emission nodes. One particularly revealing finding came from JWST's infrared dataset. During the high-intensity pulse phases, the aperture rims cooled measurably, between 3 and 5 Kelvin, then returned to baseline in between bursts. That kind of synchronized thermal response suggests energy was being routed through the apertures, not just radiating randomly. If the ELF field was a byproduct of an internal process, these apertures were acting like antenna ports or coupling points. For a moment, some hoped the triple confirmation might reveal a hidden mundane explanation, perhaps a peculiar resonance structure, or a geological mechanism no one had yet modelled. But the tighter the data aligned, the more that hope thinned. In a closed technical briefing, one ALMA systems engineer reportedly said, "This isn't background noise. It's a clock, and it's not our clock." At this point, the tone among scientists shifted from whether the signal was real to what it meant. If 3 of the world's most advanced observatories recorded the same precise ELF pulse train from the same coordinates, then the source was undeniably physical. It wasn't instrument error, it wasn't a data glitch, it was 3I Atlas. The task force moved into a phase of signal characterization, measuring stability over time. Over the course of 11 hours, the pulse drift was effectively zero. Even some of the best human-made oscillators on Earth would show measurable deviations over that window. Whatever was powering this inside 3I Atlas was either deeply stable or actively correcting itself in real time. And that's where the narrative deepened. Because objects don't correct themselves, systems do. This triple verification has since become the backbone of the entire event timeline. Every subsequent analysis of the geometry, the timing code, the trajectory rests on the foundation that this signal is not hypothetical. It's real, measured, time-stamped, and confirmed. And because it's real, the world now has to grapple with the fact that something inside 3I Atlas is coordinating. But as solid as the signal confirmation was, it raised a question no one could easily answer. what happens when a system that can produce a planetary-scale timing signal starts to move with precision? The answer would come days later, when astrometry revealed something even stranger. 3i Atlas was not drifting aimlessly. It was aiming. It began, as many major discoveries do, with a quiet spreadsheet on someone's screen. Just columns of numbers, angles, distances, frequencies, temperature gradients. But hidden in those columns was a pattern that refused to be dismissed as coincidence. Analysts reviewing the ELF timing, the aperture geometry, and the emission envelope noticed that the ratios between these independent features lined up with an almost surgical precision. At first glance, this might sound trivial. Ratios are everywhere in astrophysics. Orbital resonances, gravitational harmonics, fractal erosion patterns. But what made 3i Atlas different was the consistency. Every structural and energetic feature seemed to align with a set of repeatable mathematical relationships, as though the object wasn't just formed, it was designed according to a rulebook. The earliest clue came from the aperture spacing. 9 evenly distributed circular openings separated by exactly 40 degrees isn't just convenient geometry. When mapped into spherical harmonic space, the configuration closely matches a third-order spherical harmonic resonance pattern, the kind used in engineered antenna arrays for field stabilization. On Earth, similar configurations are employed to produce uniform radiation patterns across multiple lobes, minimizing interference while maintaining signal directionality. That would be remarkable on its own. But when researchers overlaid the emission intensity map from VLA onto the aperture model, the intensity peaks lined up almost perfectly with the harmonic nodal points predicted by electromagnetic engineering simulations. In plain terms, the energy wasn't just radiating at random, it was radiating exactly where a designer would place it to maximize coherence. The second layer came from the timing ratios embedded in the pulse sequence. The 3.7 second burst over an 89 second interval was already flagged for its match to the Earth-Jupiter mass ratio. But when this ratio was expressed in logarithmic harmonic space, it formed part of a triad with 2 other ratios found elsewhere on the object. The angular spacing of apertures, 40 degrees, the cooling differential across lattice lines, approximately 4.3 Kelvin, and the burst to interval ratio, 0.04157. When normalized, these 3 values are not random. They map onto a geometric series that converges on a constant near 0.0416. That number, though not famous like pi or phi, appears in antenna field theory as a critical point for phase-stable resonance coupling. It's used in real-world communications engineering to minimize destructive interference in multi-node networks. It was at this point that one of the independent analysts, a signal engineer by training, not an astronomer, made a sobering remark during a technical call. This isn't just pretty geometry, it's functional geometry. This thing is built like it knows Maxwell's equations. The geometry went deeper. The lattice grid that runs between the apertures isn't random either. Each straight line is positioned at angular intervals that form a nested 2:3:5 ratio, a sequence that appears in Fibonacci-derived spatial tilings often used to distribute mechanical or electromagnetic stress evenly across curved structures. It's a method humans use to design domes, waveguides, and certain advanced phased array antenna shells. When the burst pattern was analysed in frequency space, the Fourier transform revealed something subtle but critical. The signal contained clean harmonic overtones at 2 times, 3 times, and 5 times the base frequency. Natural signals, whether geological or astrophysical, usually produce messy harmonics with irregular amplitudes. The harmonics here were perfect integer multiples of the base frequency with amplitude ratios consistent across the entire 11-hour emission window. That is not how nature behaves when left to chaos. That's how engineered oscillators behave when locked to a clock. An additional clue emerged from the thermal gradient timing. When each ELF pulse was emitted, the aperture rims cooled in precise synchrony. The thermal decay curve of each aperture was identical, down to a difference of less than 0.2 seconds between peaks. This uniformity implies either a material with near-perfect thermal conduction properties or an internal system designed to equalize energy distribution in real time. Either way, it pointed to a level of internal organization incompatible with a fractured rock drifting through the solar system. Mathematicians within the task force began running pattern-fitting algorithms to check whether these ratios could arise from random processes. The result was stark, the probability of these features emerging spontaneously, with the same ratios aligning across aperture geometry, thermal behaviour, and signal harmonics, was less than 1 in 10 to the 14th power, but the pattern didn't end with static geometry, it extended to motion. When astrometric measurements from multiple observatories were combined, a tiny but unmistakable yaw-like oscillation in 3i Atlas's orientation became visible. The oscillation matched the beat frequency between the base, ELF signal, and its third harmonic. This means the object isn't just emitting, it's moving in synchronization with its own signal. It's behaving like a stabilized system with active attitude control. To be clear, no one in the scientific community is ready to publicly declare this object engineered. But behind closed doors, many acknowledge that the data aligns more with engineering principles than with natural stochastic geology. A comet doesn't align its structural nodes to electromagnetic field theory. A rock doesn't stabilize itself to harmonic resonance. Something else is happening here. For some, the implications point to an ancient probe, something designed to survive interstellar travel and activate under specific solar conditions. For others, it may be a natural artifact with emergent properties beyond what we've modelled, a sort of naturally occurring phased array born out of crystalline metallic layers. Both are extraordinary explanations, but only one fits the math with precision. One especially striking feature in the signal data is what analysts are calling the golden anchor, a faint modulation pattern buried deep in the harmonic structure, aligns with phi, the golden ratio, within 0.001 tolerance. This ratio is often used in resonant structure optimization, including in human-built spacecraft antennas and metamaterial shells. Whether this is deliberate or a bizarre coincidence remains hotly debated, but its presence adds yet another layer of mathematical symmetry to an already overdetermined system. This isn't just a strange object, it's a harmonic machine, a structure that, whatever its origin, behaves as if it was designed to minimize energy loss, stabilize its field, and align its geometry to mathematical constants. In the halls of the observatories and late-night data calls, there's a quiet unease, because math doesn't care about belief, ratios don't lie. And when multiple independent systems, electromagnetic, thermal, geometric, all point to deliberate structure, the line between coincidence and design becomes paper thin. The engineers studying these harmonics know something the public doesn't yet fully grasp. If this object was built, it's not broadcasting at random. It's executing a plan embedded in its structure, and that plan may only be at the beginning of its sequence. For months, the trajectory of 3i Atlas had been plotted, revised, and rechecked like a chess move unfolding in slow motion. Its orbit was unusual but stable, a hyperbolic approach with a close perihelion near the Sun, expected to slingshot it out of the inner solar system by early spring 2026. It was an elegant arc, clean and predictable. That changed 3 days after the ELF signal event. On the morning of October 24th, astrometric data from multiple observatories revealed something no one wanted to believe at first. The trajectory had shifted. The deviation was subtle, barely measurable against the background noise in its earliest detections, but it was real. When all measurements were cross-referenced and averaged, the object's post-perihelion vector showed a lateral displacement of 0.00012 astronomical units compared to the previous week's projections. That's only about 18,000 kilometers. But in orbital mechanics, over the span of months, that's enough to redirect a path across entire planetary systems. The real significance wasn't the size of the shift, but its direction. The vector aligned almost perfectly with the plane leading toward Jupiter's orbital path in March 2026. At first, analysts suspected an error, perhaps solar wind drag, non-gravitational forces from sublimation, or a processing mistake in the astrometric model. But sublimation outgassing, the usual culprit for a trajectory drift in comets, would produce chaotic, uneven acceleration. This wasn't chaotic. It was clean, linear, controlled. What startled orbital modelers most was that the timing of the shift matched the ELF signal event almost to the hour. The signal began late on October 21st and ended early on the 22nd. The first detectable deviation in trajectory was time-stamped October 23rd, when high-resolution radar tracking showed a tiny but statistically undeniable change in outbound velocity vector. It was as if the signal window wasn't just a broadcast, but a maneuver sequence. The possibility of an internal propulsion mechanism was suddenly on the table. To explore that, analysts went back to the ELF event window. They cross-correlated the pulse amplitude peaks with the trajectory data. What they found stunned them. The highest amplitude bursts, those at the beginning of the emission cycle, align exactly with the direction of the shift. If the ELF event wasn't just electromagnetic noise but the byproduct of an internal force generation system, then the October 21st signal may have been the ignition of a maneuver. An important detail deepened the mystery. If the object had vented gas, the rotation rate should have changed. Sublimation torque is not subtle. Even a slight venting would measurably alter its spin. But the rotation remained locked at 11.3 hours, unchanged within the margin of error. No measurable precession, no wobble. That implies the force was applied symmetrically, without destabilizing the spin, something that's nearly impossible for natural vents but standard for controlled thrust systems. There was also no outgassing plume. Instruments designed to detect volatile releases, infrared and ultraviolet, saw nothing. No jets, no thermal bloom, no spectral lines of water or carbon compounds. The maneuver, if that's what it was, happened in silence. By October 25th, the trajectory correction models were finalized. The new orbital solution placed 3i Atlas on a path that threads through a narrow gravitational corridor, an efficient slingshot that requires remarkable precision to exploit. Engineers familiar with interplanetary navigation recognized the pattern immediately. This wasn't the kind of corridor an object stumbles into. It's the kind of path a spacecraft would choose to maximize gravitational assist. When this realization circulated through private briefings, the tone changed dramatically. What had been dismissed by some as an odd comet with a strange signal was now behaving like a navigationally competent body. The timing of the burst event, the thrust-like vector, the precision of the corridor, it formed a chain too clean to ignore. Jupiter's magnetosphere isn't just a gravitational well, it's a massive electromagnetic structure, dwarfing anything else in the solar system aside from the Sun itself. If the ELF burst was tied to the Earth-Jupiter mass ratio, and the object adjusted its path immediately after, the implication is clear. The signal may have been part of a pre-programmed approach sequence aimed at Jupiter's magnetospheric environment. This triggered what insiders are quietly calling a Level 2 contingency analysis, a rare escalation typically reserved for near-Earth objects with anomalous behaviour. It's not about threat assessment alone, it's about understanding whether the object's movement is governed by deterministic control. One of the more chilling details in the astrometric data was the lack of deceleration. Normally, after a sublimation-driven thrust, the trajectory curve slowly drifts back toward equilibrium as the volatile source depletes. Here, the deviation held steady. Whatever caused it acted once, cleanly, and then stabilized. Like a burn maneuver, like a course correction. This also meant something else. If 3i Atlas is capable of changing its trajectory even slightly, its future positions are not fixed. Traditional orbital prediction methods assume passive bodies. This one clearly isn't passive anymore. Some officials have quietly drawn parallels to early moments in other anomalous encounters, where natural explanations were stretched thin against increasingly structured behaviour. But here, unlike with distant transient detections, the object is inside the solar system, moving toward a major planetary body with weeks of lead time to observe its every step. By late October 26th, the language in technical bulletins shifted. Words like non-gravitational acceleration were replaced with directed impulse event. Phrases like unmodelled natural outgassing gave way to controlled vector shift. And in the private channels where the data analysts speak freely, a single sentence began to circulate. This thing didn't just talk, it moved. It was no longer a mystery object with a strange signal. It was now a manoeuvring body on a trajectory toward Jupiter, and whatever awaits in its magnetosphere may not be random at all. Once the orbital adjustment was confirmed, something remarkable appeared on the mission timeline charts. The new trajectory of 3i Atlas wasn't just heading vaguely toward Jupiter, it was threading itself through a precisely timed corridor that aligns with the operational window of JUICE, the European mission currently orbiting and conducting flybys in the Jovian system. According to updated astrometry, the object's closest approach to Jupiter is projected for March 13th, 2026, with a plus or minus 4-day uncertainty window. That alone would be significant. But JUICE's next major periapsis manoeuvre around Ganymede is scheduled for March 16th, 2026, right inside that window. The alignment wasn't just close, it was uncomfortably precise. Jupiter is vast. Its magnetosphere is the largest structure in the solar system, extending millions of kilometers. But the corridor 3I Atlas has now entered isn't arbitrary. When plotted against Jupiter's magnetic bow shock and the predicted positions of JUICE's orbit, the object's inbound vector crosses near the same sector of magnetospheric space JUICE will occupy in mid-March. Statistically, this is extremely unlikely. The object could have veered anywhere in the plane of the ecliptic after perihelion. Instead, it's threading a path toward a specific region at a specific time. This realization set off an immediate chain of communications between the European Space Agency, NASA, and several planetary defense coordination offices. On paper, there's no collision risk. The closest approach between JUICE and the predicted 3I Atlas path remains more than 1.8 million kilometers, a vast distance. But operationally, that's inside the same electromagnetic environment. If 3I Atlas is emitting or interacting with Jupiter's magnetic field, JUICE could end up flying through whatever this thing does next. Internally, engineers began running field interference simulations. JUICE's magnetometer suite is extremely sensitive. Even weak ELF or VLF activity at close range could distort measurements. But what's more concerning is the possibility of induced resonance. Jupiter's magnetosphere is already home to powerful natural radio emissions, decometric bursts, auroral ELF signatures, and plasma wave structures. Introducing a stable external ELF oscillator into that environment could amplify or modulate those waves in unpredictable ways. In technical briefings, mission controllers began referring to 3I Atlas as an unplanned participant in the JUICE observation cycle. That phrase conceals the deeper implication. If the object is actively maneuvering, and if its timing is deliberate, then its proximity to JUICE might not be a coincidence at all. One of the more chilling calculations came from a trajectory specialist working with ESA's flight dynamics team. They modelled the propagation of the October 21st trajectory shift forward in time. Even a small change in vector could have sent the object anywhere in the Jovian system, but the corridor it chose passes through the lowest magnetic turbulence zone on the inbound side of Jupiter's bow shock, a narrow, stable pocket often used as a preferred insertion corridor for spacecraft approaching the planet. JUICE was never meant to have company in that corridor. Now it will. Another anomaly emerged when analysts examined the object's velocity relative to Jupiter. Its inbound velocity, after perihelion acceleration, is projected to be around 19.6 kilometers per second, which places it well within the capture resonance band of Jupiter's outer magnetosphere. That doesn't mean it will be captured. The object's hyperbolic excess velocity is too high for an easy orbital insertion, but it does mean the object will linger longer inside Jupiter's electromagnetic influence than a purely ballistic pass would require. In other words, the path is tuned to maximize interaction time. And then came the comparison. The flight path of JUICE and the flight path of 3I Atlas, when overlaid, resemble two threads crossing the same knot in space-time, different altitudes, different angles, but the temporal overlap is undeniable. It's as though the object selected its corridor knowing exactly when and where the spacecraft would be. Skeptics pointed out that this might still be coincidental. Jupiter is a natural attractor. Many objects pass through its sphere of influence each year, but those are stochastic trajectories. They don't line up with active spacecraft schedules. The odds of a purely natural object making a trajectory correction that places it inside the same corridor at the same time as a flagship ESA mission are vanishingly small. In closed-door sessions, some ESA analysts raised an uncomfortable scenario. If the object is transmitting or activating systems in Jupiter's magnetosphere, JUICE might detect data or signatures never intended for us. In that case, the mission may become an involuntary observer of something far larger. Others, more pragmatic, pointed out that JUICE's instruments could provide unprecedented readings if the encounter happens as projected, essentially turning the spacecraft into a front-row witness to whatever happens next. The ELF signal data has already been loaded into JUICE's flight software library. Mission planners are reconfiguring telemetry priorities to maximize listening modes during that window. Originally, JUICE was supposed to focus on magnetospheric structure mapping and Ganymede auroral emissions during that orbit. Now those plans are quietly being rewritten. If 3i Atlas maintains its trajectory, JUICE may be the first human instrument to witness direct interaction between a maneuvering interstellar object and a giant planet. Behind the scenes, several orbital mechanics experts are pushing a more speculative theory. This may not be about us at all. The object may have selected this corridor centuries ago, long before JUICE existed, simply because it is the most efficient gravitational path through the Jovian system. Its alignment with the spacecraft could be nothing more than a disturbing side effect of precision. But others aren't so sure. The Earth-Jupiter mass ratio encoded in the burst sequence, the timing of the trajectory shift, the selection of a stable approach corridor. It all fits together with unnerving neatness. In the last mission briefing of October, one flight controller reportedly said quietly, "We're not chasing it. It's coming to where we already plan to be." What happens in March 2026 will depend on what 3i Atlas does inside that corridor. But from now on, every maneuver, every pulse, every subtle deviation is being watched with military precision. Because this time, we won't be looking from afar. Juice will be in the neighbourhood. By the time the ESA-JUICE alignment became clear, attention had swung back to one of the most peculiar and persistent features of 3i Atlas. The 9 circular apertures arranged with mathematical precision around its midsection. They were there before the signal, they were there before the manoeuvre, but their role remained unresolved, and the closer the object drew to the Sun, the more the pattern itself began to look less like a superficial curiosity and more like a functional key to the entire structure. The number 9 is not arbitrary in engineering. On Earth, phased array systems frequently use odd-numbered nodes to achieve uniform field distribution. With an odd number of emission points, there's always a central phase reference and a symmetric balance of phase lobes. In simpler terms, 9 nodes make for a clean, stable signal. But what intrigued analysts wasn't just that the apertures were evenly spaced. It was the fact that they appeared to align dynamically with planetary harmonics. Here's how it unfolded. Analysts ran simulations to compare the aperture geometry with known resonance frequencies of the Jovian system, frequencies generated by the interaction between Jupiter's magnetosphere, its moons, and solar wind. When they overlaid the harmonic bands with the spacing of the apertures and the frequencies present in the ELF burst, a startling alignment emerged. The spacing of 9 apertures corresponds almost perfectly to the dominant harmonic nodes in Jupiter's magnetospheric ELF spectrum. This isn't speculative pattern hunting, it's hard, measurable data. Jupiter's magnetosphere naturally oscillates at specific ELF and VLF frequencies, among them a dominant mode at 0.27 Hz, which is exactly the same frequency at which 3i Atlas emitted during its October 21st burst. Those oscillations are usually weak and chaotic, but if an external source were tuned to resonate with those frequencies, it could theoretically amplify or stabilize them, much like how a tuning fork can make a nearby string vibrate in sympathy. And 9 equally spaced emission points would be one way to accomplish that. This opened an entirely new branch of discussion inside the task force. What if the apertures are not communication ports at all, but coupling points? A planetary resonance interface is not science fiction. Human-built spacecraft already exploit resonance to slingshot around planets, or amplify signal range by bouncing electromagnetic energy off existing fields. But the precision with which 3i Atlas's aperture array matches the Jovian harmonic grid is orders of magnitude higher than what random geometry would produce. Thermal monitoring added weight to this theory. During the October 21st emission event, all 9 apertures showed synchronized temperature drops and recoveries. Not sequential, not scattered, but in-phase cooling. This implies that they are either connected to the same internal system or designed to act in perfect unison. Thermal engineers know this signature well. It's what happens when an array of emitters is linked to a single source. Then came a more granular observation. By stacking multiple high-resolution infrared datasets, analysts discovered that the edges of the apertures are not identical. Each one has a slight variation in diameter, differences on the order of just a few centimeters. That might seem negligible, but in field emission systems, such variations can create phase differentials used to control the shape of a wavefront. 9 nodes, each slightly offset, could shape an emission beam pattern that's anything but random. One model, proposed quietly by an independent antenna physicist, suggests that the aperture configuration could produce a targeted lobed pattern, something like a 9-petal structure. If activated inside Jupiter's magnetosphere, it could resonate across multiple field lines simultaneously, potentially creating standing waves. This wouldn't require immense power, it would only require precision, which 3i Atlas seems to have in abundance. And the number 9 itself isn't meaningless in resonance networks. 9-node systems are known to minimize destructive interference when coupling with external oscillators. In this case, the external oscillator isn't another machine, it's Jupiter, the single largest electromagnetic environment in the solar system. If 3i Atlas was designed to lock onto a planetary field, this is exactly the kind of structure one would expect. There's also a more subtle aspect, the angular alignment of the apertures with the object's rotational axis. Observations show that each aperture passes through its maximum thermal and signal coupling phase when facing a specific celestial azimuth. When plotted against the ecliptic, that azimuth lines up with the approach vector toward Jupiter's subsolar point, the region where the magnetosphere's pressure is at its peak. In effect, the object seems to be turning its most sensitive surface toward the part of Jupiter's magnetosphere that would yield the strongest resonance response. If this were an engineered device, the intent would be clear: not to send a message across the cosmos, but to interface locally with the largest planetary electromagnetic structure in range. If it's natural, then the coincidence would be staggering. Still, there are competing interpretations. Some geophysicists maintain that the apertures could be vent structures of a highly regularized crystalline formation, a kind of interstellar geode whose internal conductive layers create resonance as a byproduct. Others argue it could be a passive receiver, not an emitter, aligning itself automatically through some unknown physical feedback process. But among antenna specialists, there's little ambiguity. One senior analyst phrased it starkly: 9 nodes, resonant frequency match, planetary harmonic lock. If this isn't built to couple to Jupiter's field, then nature just wrote Maxwell's equations on a rock for fun. If the object is indeed preparing to resonate with Jupiter's magnetosphere, then the March 2026 alignment isn't just a flyby, it's a staged interaction. The ELF burst in October may have been nothing more than a calibration event, a way of aligning its array before approaching the true target. As March approaches, every instrument we have will be pointed at those 9 apertures, because if they light up again and lock onto Jupiter's field the way the data suggests, this won't be a passive encounter. It will be a synchronized event between a maneuvering interstellar object and the most powerful planetary magnetosphere in the solar system. And once resonance begins, control may shift from observation to reaction. Whatever happens next will unfold in real time, with JUICE already in the neighborhood. For months, the story of 3i Atlas had been dominated by words like strange, unusual, and anomalous. But as the data accumulated, from ELF emissions to aperture geometry to its subtle course correction, one question loomed larger than any other. Where is the energy coming from? Natural objects have natural limits. A comet sublimates, vents gas, spins a little faster, and its energy footprint is ultimately constrained by how much sunlight it absorbs and how many volatiles it carries. But 3i Atlas has been behaving as if that constraint doesn't apply. Its energy budget, measured across multiple systems, exceeds what a typical comet could sustain by several orders of magnitude. The starting point of the energy audit was the October 21st ELF burst. At 2.3 megawatts of sustained output, this isn't an earth-shaking figure compared to stars or even planetary fields, but it is massive for a single object of its size, an object with no visible outgassing, no ion tail of consequence, and no detectable thermal plume. More importantly, the signal remained stable for nearly 11 hours, showing no signs of depletion. That alone ruled out most volatile-based explanations. Sublimation vents are messy. They fluctuate wildly with solar flux. They sputter, roar, and fade. This was clean. Analysts began calculating how much solar energy the object could be absorbing at its distance from the Sun. Its effective cross-section is roughly 500 meters wide at its longest axis. Even assuming near-perfect albedo absorption, the maximum solar power available at that distance would be well under 1 megawatt, and that's if every square meter of the surface was being used with 100% efficiency. It's not. yet the ELF emission alone exceeds that upper limit. In other words, it's outputting more power than it's taking in. This energy imbalance only deepened when researchers accounted for trajectory shift. The clean vector change observed after the ELF burst requires a finite impulse, and that impulse requires energy. Even if the thrust was minimal, changing the trajectory of a mass that large by measurable degrees would require a total energy expenditure in the terajoule range. If the maneuver was performed without detectable mass ejection, then the energy had to come from inside the object. That's when analysts began mapping potential internal energy sources. They considered radioactive decay, trapped solar charge, piezoelectric discharge, and exotic but known geophysical phenomena. One by one, the options fell away. Radioactive decay. There's no gamma signature, and the thermal signature remains too cold for significant radioactive heat. Electrostatic charge accumulation. The amount of charge required to sustain a 2.3 megawatt ELF broadcast would create field instabilities detectable from Earth. None were observed. Sublimation pressure. No jets, no tail, no torque, nothing. The math simply doesn't work for passive explanations. The most conservative hypothesis left standing is induction storage. The idea that the object accumulated charge over long interstellar travel, storing energy like a colossal capacitor and releasing it at perihelion. But this requires the object to behave as a structured conductor, with internal separation of charge and a controlled discharge mechanism. And that leads back to the thing most astronomers are uncomfortable saying out loud. This doesn't behave like a comet. It behaves like a system. This is also where the 9 apertures and their synchronized temperature drops return to the foreground. If the ELF field isn't being generated passively, those apertures may be acting as controlled emission ports. Thermal models show that for their temperature to fall and recover so uniformly, something inside must be routing power to them with extraordinary precision. This is the kind of regulation one would expect from an engineered energy distribution network, or from a very, very exotic form of self-organizing physical system we've never seen before. An even more concerning aspect emerged when energy auditors calculated the efficiency curve of the ELF emission over time. The signal maintained amplitude even as the solar wind fluctuated, but the internal thermal response actually became more stable during periods of high solar interference. That's backward. Most natural signals degrade when the environment becomes noisy. Here, the object seemed to tighten its own output to compensate. That's an adaptive response. Either the structure possesses self-regulating physical properties we don't understand, or it is actively managing its energy flow. This adaptive quality also appeared during the maneuver event. In a typical natural outgassing scenario, the rotation rate of a body changes measurably when thrust is applied, but 3i Atlas kept its 11.3-hour spin rate absolutely fixed. The only way to do that is to balance thrust across multiple points. A deliberate action, not a random jet, and balancing thrust costs more energy, not less. Whatever is inside is not only the ability to generate or release stored energy, but to control how and where it's applied. The deeper analysts went, the more they encountered a hard wall. The energy budget is too high, too stable, and too well behaved for a passive object. One theoretical paper circulating in draft form within the International Monitoring Network outlines a possibility that has made even cautious voices pause. The object could be running on a closed-loop internal energy system, something akin to an electromagnetic flywheel. It may have stored energy during its interstellar transit, waiting for the right environmental trigger to unlock a controlled sequence. October the 21st may have been that trigger. There's also a darker possibility that what we're seeing now is only a fraction of its energy capacity. The 2.3 megawatt ELF emission might not be its main output at all. It could be an auxiliary channel, a timing beacon or synchronization signal, with far larger reserves held in silence. If the trajectory maneuver was a single impulse, it may have used a tiny fraction of that stored energy. Which raises a simple but unsettling question. What happens when it uses the rest? The Jupiter approach corridor is the perfect environment to test this. Jupiter's magnetosphere is effectively an energy amplifier, a massive plasma structure that can boost or resonate with external fields. If 3i Atlas couples with that field using its 9-node array, the energy signatures could surge dramatically. In that scenario, its true energy capacity wouldn't just be detectable, it would be unavoidable. This is why, behind closed doors, the tone of technical briefings has shifted from observation to risk mapping, because if an object of unknown origin can maneuver, generate power, and align itself with a planetary magnetosphere, we are no longer describing a passive astronomical event. We're describing an active energy system entering an environment we can't control. One physicist working on the signal modelling reportedly put it in blunt terms during a late-night call. We're not looking at a rock that stumbled into a power surge. We're looking at a power source that's been waiting for the right moment to turn itself on. At this stage, the natural explanations are thinning fast. What remains is either a natural phenomenon, unlike any we've ever documented, or the first close-up example of a deliberate controlled system operating within our solar system. The Jupiter window isn't just a milestone on a timeline anymore, it's the next stage in whatever sequence 3i Atlas is following, and that sequence is running on a power curve we still don't understand. Even as the anomalies surrounding 3i Atlas grow harder to explain, the scientific community has not abandoned caution. Every extraordinary claim must be tested against the simplest physical explanations first. It's a fundamental rule in science, one that has saved researchers from countless false alarms over the decades. And in the early days after the E-elf burst, there was a quiet determination to ground the story in known physics, to find an explanation that would make the object less mysterious, not more. The first line of thought focused on the idea of a natural electromagnetic dynamo. If 3i Atlas contained a metallic or partially conductive core, then its slow rotation through the heliospheric magnetic field might generate a weak Aleph signature. This concept wasn't without precedent. Several Jovian moons produce induced fields through interactions with their parent planet's magnetosphere, and even terrestrial experiments have shown similar principles at work. For a moment, this seemed like the cleanest explanation. No need for technology, no hidden mechanisms, just a conductive rock spinning in space. But the more carefully the signal was examined, the more the theory unravelled. The ELF emission was not weak or chaotic. It was powerful, narrowband, and astonishingly stable. Induction from a passive body can't maintain a fixed frequency for 11 hours straight while resisting solar wind fluctuations, and it certainly can't align perfectly with an Earth-Jupiter mass ratio. A second explanation grew out of the aperture geometry. Some speculated that the 9 circular openings could be the result of exotic crystalline formation, a natural geode, forged during long interstellar travel that happened to produce resonant electromagnetic properties. Under this hypothesis, the ELF burst was just the structure ringing like a giant bell as thermal stress built up near perihelion. On paper, it sounds imaginative but not impossible. Cosmic crystalline lattices do exist. Meteorites carry them. Some can conduct. Yet, crystalline resonance is messy. It drifts with temperature. It fractures unevenly. It doesn't produce a perfectly timed planetary matched pulse train. The apertures of 3i Atlas, instead of responding independently like natural cracks, cooled in flawless synchrony. Every thermal curve was identical, down to fractions of a second. No crystal formation behaves like that. Then there was the sublimation argument, the oldest and most familiar explanation for cometary oddities. Many insisted that the subtle course change after the signal event could still be explained by invisible outgassing. Perhaps the object released a jet of volatiles that nudged it toward the Jupiter corridor without leaving obvious thermal traces. But that theory fell apart as soon as the rotation data was analysed. Real jets create torque, they destabilise spin rates. Yet 3i Atlas kept its 11.3-hour rotation absolutely locked. The vector shift was linear and clean, with no detectable plume, no deceleration, and no follow-on drift. It behaved more like a controlled impulse than a natural vent. There are other softer theories: solar wind coupling, plasma sheath effects, induced magnetism, each of them fragile in its own way. All share the same fatal flaw. None of them can explain the combination of events. A passive body can sometimes produce a signal. A fractured object can sometimes shift its path. But a passive body producing a stable ELF emission, then executing a precise trajectory adjustment without a visible plume, and doing all of it with aperture geometry that mirrors Jupiter's harmonic grid. That stretches naturalism past its limits. This doesn't mean scientists are ready to declare the object artificial. No serious agency is willing to cross that line lightly. There's a stubborn hope that some undiscovered, deeply exotic natural process is responsible. some property of conductive interstellar materials we've never seen before. It's the last bastion of caution. But privately, even among those clinging to natural explanations, the language is shifting. The words coincidence and alignment are being used less. Words like sequence, pattern, and timing are starting to take their place. There's a deep, quiet unease in this change. Natural objects don't behave like this. They don't generate precision signals. They don't shift course cleanly. They don't align their geometry to planetary harmonics as if preparing for an interaction. And yet, for now, the official statements remain conservative. Analysts talk about unmodelled natural dynamics. They call the ELF burst unusual but not unprecedented. They describe the apertures as regular structures of undetermined origin. But behind that careful language is something else, the growing recognition that the natural explanations are wearing thin. Every day that 3i Atlas stays silent after its activation event, every kilometre it draws closer to Jupiter, makes it harder to believe this is just a rock caught in an unlucky coincidence. This science is trying to hold the line. The data keeps pushing it back. Every complex story has a moment where everything quietly pivots. For 3i Atlas, that moment was October 21st, 2025. Before that date, the object was strange, an elongated body with unusual reflectance patterns and an orbit worth watching, but still catalogued like any other interstellar visitor. After that night, it became something else entirely. The ELF signal didn't just draw a line in time, it split the narrative in two. Everything observed since then, the synchronized thermal behavior, the course correction, the harmonic geometry, the Jupiter alignment, can be traced back to that precise activation window. The shift wasn't loud or explosive. There was no sudden flare, no visible transformation, no tumbling or fragmentation. It was quiet, almost deliberate. A pulse sequence began, crisp and exact, as if a clock buried inside the object had been counting down to that moment for years, perhaps even for centuries. In hindsight, what made the event so striking wasn't the sheer power of the ELF burst. It was its timing. The burst happened just as 3i Atlas crossed a heliocentric distance threshold that orbital modelers now recognize as a kind of trigger zone, a range where solar intensity, plasma density and rotational phasing all align to create a stable environmental envelope. For ordinary comets, this threshold simply means more sunlight, more heat, and the start of outgassing. For this object, it marked something entirely different: activation. Everything about the burst suggests internal coordination: the clean onset, the stable plateau, the sudden stop. It didn't fade out the way a natural signal does when a process runs out of energy. It cut off like a system shutting down after a timed sequence. That distinction, fading versus ending, is what changed how analysts view the event. The timing nexus, as some quietly call it, has become the focal point of every model. When the ELF signal began, the object had just entered the inner solar system's high-density solar wind corridor, where magnetic field lines run more tightly and predictably. The apertures on its surface were aligned with rotational precision, and the signal was phase-locked to its spin. Within 24 hours of the last pulse, its orbital vector shifted. It was as if the ELF burst wasn't the message, it was the command, a maneuver command, a synchronization handshake, the beginning of a sequence that's still unfolding. This moment also exposed the limits of natural explanations. If the burst had appeared at random, analysts could have ascribed it to thermal stress or some resonant accident. But the fact that it occurred exactly at a predictable solar distance and lasted precisely 11 hours is statistically extraordinary. That length of time wasn't arbitrary either. It corresponds exactly to one full rotation of the object, one cycle, one event. There's a growing view inside the signal analysis community that October 21st wasn't just when the object did something. It may have been when it woke up, or more precisely, when it followed a schedule. Some refer to it as Phase 1, borrowing the language of software rather than astrophysics. That's not how scientists like to talk about space objects. Yet the data forces them closer to that language than they're comfortable with. The timing of the burst also matches broader celestial alignments. The Earth-Jupiter angular separation on that date created an unusually clean gravitational corridor along the ecliptic. The object's post-burst vector now traces directly through that corridor. To some orbital dynamicists, this looks less like coincidence and more like navigation. It's as if the event wasn't just internal activation, It was the moment 3i Atlas locked onto a predetermined path. Every signal since then has been measured against this inflection point. Minor thermal fluctuations are analysed in reference to the original ELF waveform. Orbital shifts are plotted against the original trajectory deviation, and perhaps most tellingly, the timing of the Jupiter approach, projected for March 13, 2026, fits neatly into a 5-month interval, which aligns precisely with the harmonic modulation embedded in the original burst sequence. None of this proves anything on its own, but together these alignments build a picture that's increasingly hard to wave away. For mission planners at ESA and NASA, this date has quietly become a clock. Whatever happens in March begins with what happened on October 21st. JUICE's flight path adjustments, signal monitoring campaigns, and plasma diagnostic schedules are all now structured around that timeline. It is the heartbeat they are listening for. For the skeptics, the inflection point is uncomfortable. They've long argued that anomalies scatter over time, growing less coherent the closer we look. But this one hasn't. Every new data set folds back into that night like threads converging on a single knot. Instead of unravelling, the pattern is tightening. There's a quiet, almost reluctant consensus forming beneath the surface of official statements. 3i Atlas isn't reacting randomly. It's on a timeline. And October 21st was the first clear, measurable tick of that timeline. The moment the background noise turned into a structured sequence. What that sequence leads to is still an open question. But everyone studying it knows one thing. It started here. This was the hour the story of 3i Atlas stopped being strange and started being deliberate. The closer 3i Atlas moves along its new trajectory, the less the debate revolves around what it is, and the more it revolves around what it could do once it enters Jupiter's magnetosphere. At first, the idea of risk mapping was limited to orbital mechanics, tracking its path, calculating closest approach, and assessing collision probabilities with JUI, CE or the Jovian moons. But the object's behaviour has already broken the template. It's not following the pattern of a passive body, and that means risk analysis can no longer be just about orbital paths. It has to account for interaction. Jupiter is not an ordinary destination. Its magnetosphere is so large it would engulf the Sun if made visible to the naked eye. It's a storm of plasma, radio waves, charged particles, and electromagnetic pressure that can bend or break anything unprepared to withstand it. Most natural bodies drift through this field without leaving a fingerprint, but a system capable of producing a stable ELF emission at Jupiter's resonant frequencies might not just pass through that environment, it might amplify it. Or worse, it might use it. In internal briefings, analysts have begun sketching out several interaction scenarios, not as predictions but as contingency maps. The mildest scenario is that 3i Atlas enters the Jovian field, resonates briefly, and continues on its way, leaving behind little more than a ripple of intensified plasma activity. That would be extraordinary from a scientific standpoint, but harmless. The second, more complex scenario is that the object locks into the magnetosphere, synchronizing its 9-node aperture array with the planet's field lines. If that happens, the event could generate electromagnetic surges on a scale we've never observed before. Jupiter's magnetosphere already emits natural ELF and VLF bursts powerful enough to be detected from Earth. If an external, precision-tuned oscillator joins that system, the energy levels could spike in unpredictable ways. Some researchers describe this not as a collision of forces, but as the insertion of a key into a lock. Once that happens, the planet itself could become a kind of amplifier, turning a contained emission into a planetary-scale resonance. No one knows what the upper bounds of such an event might be, because nothing like it has ever been recorded. There's also the unnerving question of duration. The October 21st ELF burst lasted exactly one rotational cycle, but if the Jupiter encounter is the object's intended target, the emission might not last hours, it might last days. And in a magnetosphere of that scale, days are enough to imprint vast disturbances across the entire field. Some magnetohydrodynamic models suggest that if the object maintains its harmonic lock, the energy could propagate along Jupiter's magnetic field lines out toward the heliosphere, a resonance wave that wouldn't stay local. This is where planetary defense agencies quietly enter the conversation, not because they believe the object poses an immediate physical threat to Earth, but because large-scale electromagnetic events in Jupiter's system can cascade. The Jovian magnetosphere connects to the solar wind in ways that influence the broader heliospheric environment. An amplified ELF event could, in theory, affect charged particle flow, magnetic alignment, and even the background noise levels of interplanetary communication networks. If it's loud enough, we'll hear it across the solar system. Another layer of the risk analysis concerns JUICE. If the object emits again at close range, the spacecraft will be inside the field envelope. Its instruments are sensitive enough to record the event in exquisite detail, but they're also vulnerable. Overload scenarios are already being simulated. Certain magnetometer and plasma wave instruments might need to enter protective mode during the encounter if the signal spikes beyond expected levels. ESA planners have started to quietly prepare for that possibility, even as they avoid making public statements. The risk mapping isn't just technical, it's psychological and geopolitical too. If the event is spectacular enough, if it lights up Jupiter's magnetosphere in a way no one can ignore, there will be no containing the narrative. This isn't a telescope-only anomaly anymore. It's a potential planetary-scale signal that could be visible across multiple sensor networks, civilian, scientific, and military. In some scenarios, the object's emission could even be detected by low-frequency arrays on Earth without specialized equipment. The story would break everywhere at once. Inside the Planetary Defense Coordination Network, the tone has shifted from skepticism to strategic calm. No one is talking about threat levels in public. But behind closed doors, every agency is running their own models, asking the same uncomfortable questions. What happens if this isn't passive? What happens if the ELF burst over Jupiter isn't just a signal, but part of a sequence? And what happens if that sequence doesn't end at Jupiter? This is why October 21st wasn't just an astronomical event, it was an operational one. The object has already demonstrated 3 capabilities that no passive body should have. It generated a clean signal, it altered its course, and it aligned with a planetary harmonic grid. Whether it does anything else is still an open question. But the Jupiter encounter is no longer just a scientific curiosity. It's a strategic waypoint. There's a sense, unspoken but felt, among those studying the data, that once 3i Atlas enters that field, the clock will start ticking again. Whatever timeline began in October may reveal its second chapter there. It might be quiet, it might be spectacular, it might be something no one is prepared for, but the encounter is no longer theoretical. It's scheduled by physics itself. Jupiter will be waiting, and so will we. When the first ELF pulse rippled out from 3i Atlas on October 21st, 2025, it was just a line on a spectrograph. Faint, precise, almost easy to miss, but it marked a boundary that can't be uncrossed. In that moment, an object we'd treated as just another interstellar fragment revealed itself to be something far more deliberate. Everything that followed, the geometric shell, the harmonic timing, the course correction, the Jupiter alignment, was built on the foundation of that quiet, unwavering signal. This isn't the first time humanity has pointed its instruments at something we didn't fully understand. But this time, the data hasn't scattered or faded with scrutiny. It has tightened. Every measurement folds back into a single thread, weaving a pattern too clean to ignore. The ELF burst wasn't an isolated anomaly. It was the first heartbeat of a sequence, a system waking up, or perhaps simply resuming something that began long before we were watching. Jupiter is no ordinary waypoint. Its magnetosphere is a vast ocean of energy, deep, turbulent, and alive with electromagnetic tides. Most objects fall through it silently, unremarkable in the storm. But 3i Atlas isn't falling. It's aiming. It's threading a corridor that intersects with one of the most stable harmonic zones in the Jovian field, timed to coincide almost exactly with a major mission window. That's not the signature of chaos. That's choreography. If the object couples with Jupiter's field, the encounter will not be subtle. It could light up the magnetosphere with structured resonance, pushing a planetary system into a state we've never witnessed before. Instruments across the solar system, from orbiters to ground arrays, would register it, not as noise, not as a burst of randomness, but as a coherent, deliberate event. And the strangest part of all is how inevitable it now feels. Every day brings it closer to that point of contact, and with each kilometre it travels, the natural explanations fray a little further. A comet doesn't broadcast planetary ratios. A crystal lattice doesn't execute precision manoeuvres. A piece of drifting rock doesn't align itself with the largest magnetic field in the solar system, like a key turning toward a lock. Something is unfolding here, something larger than a single signal or a single object. This isn't a race, it's a timeline. It began quietly, with a single structured pulse, and it's heading toward Jupiter on a schedule that hasn't shifted by a second. Whether that sequence ends there or only begins is impossible to say. Maybe this will be just another mystery added to the list. Or maybe, when it crosses the magnetosphere, the world will hear something it can't unhear. For now, the sky's silent again. No more pulses, no more course changes, just a dark shape gliding toward its next waypoint, carrying whatever purpose was set in motion long before we knew to look for it. October 21st was the first tick of the clock. March 2026 will be the next, and somewhere between those two moments, a line will be crossed again. Whatever happens out there, it won't be random. It will be the second movement in a sequence that has already begun. All we can do is watch and wait for the silence to break.